Welcome. I wanted to say something about an amazing theorem, the Maze Theorem. It's something I encountered when looking at torsion. And indeed, there will be a result. It's already mentioned in my blog, and also last time I mentioned that last week. There is a kind of a nice formula for torsion in the case of two-dimensional spheres. So a two-dimensional sphere is a graph, finite simple graph, like this one, where every unit sphere is a circular graph of with four or more elements. And so this has a manifold structure. So locally, this looks like a manifold. And also when you take one vertex away, it should become contractible. We have defined that last time. It's a very nice definition for spheres. You can do that in any dimension. And also what we do here can actually be generalized for arbitrary dimensions, but we are just focusing on for two-dimensional spheres. And in two dimensions, actually in general, you have a dual graph. The dual graph has the vertices, as vertices the faces. So in this case, the icosahedron has the dual graph, which is the dodecahedron. This is no more a sphere, as I said last time. So the unit sphere here is just a three-point graph. This is not a circular graph. So you would have to attach these faces and kind of do a CW complex construction. But we are not doing that. So this is a dual graph, again a graph. And what we have is we can look at the number of spanning trees. So that's what we are going to look at. Spanning tree is an embedded tree in the graph, which is of course connected by definition, but which covers all the vertices. And so we can count them. This is what physicists are very interested in. Partition function, when you count all these spanning trees. This is I call this T of G, and so this has an algebraic description in terms of the Kirchhoff matrix, which also has been mentioned last week. The Kirchhoff matrix is just a zero-dimensional Laplacian. It's the divergence of the gradient. So this is the divergence, the gradient, and so D is this discrete matrix, which is given as soon as you have an orientation fixed on every of the simplices, which is quite arbitrary. So, but this matrix has been introduced in the 19th century by Kirchhoff, and it's a very important thing. It's the zeroth part of the Hodge Laplacian, so there is more general. We have the LKs, which I have mentioned last time. The LKs are the form Laplacians on k-dimensional of k forms, and so this is just a zero-dimensional version. And torsion we have defined last time. I painted over it. So this is k times minus 1 to the k plus 1. So this is the torsion which we have seen. And in the case of two-dimensional spheres, simplified two-dimensional cases in general, this simplifies as the determinant of L0 over the determinant of L2, and there will be a duality which tells us that this is actually the Kirchhoff Laplacian of the dual graph. So that's a symmetry. I'm very excited about this topic because there are three different symmetries which appear here. First of all, there is the McKean-Singer symmetry, which is actually needed here for this reduction. McKean-Singer is a symmetry which is in general true for any network, any graph. And so we will look at that. And then there is a Poincare duality, symmetry again, but completely different thing, which only holds for discrete manifolds. And then we have a third symmetry, which is the tree symmetry, which I'm talking about today, which actually holds in general in arbitrary dimensions for spheres, which tells something about trees in the graph and the dual graph. Also, this is very subtle and doesn't hold for all networks. It holds actually not even for manifolds in general. Completely wrong, even if you make, if you take here just one refinement of a triangle, it's already completely wrong. And so you measure it. You can do that with a computer, and I can show you some examples how you compute torsion, how you actually compute for arbitrary spheres. You can arbitrary graphs. You can compute all these notions which we are going to look at. So it's all quite elementary and related to topics which are very ancient. You know, the Greek mathematicians have looked at this polyhedra, and more generally at spheres, and we can look at discrete spheres in graph theory in arbitrary dimension. But today I just want to focus on the two-dimensional case, and I want to start with some linear algebra, which I'm very excited about because I worked on that myself. So it's the Cauchy-Binet theorem. So the Cauchy-Binet theorem is a theorem for determinants, and I generalized it for pseudo-determinants in 2013. It was published in 2014. I'm very proud about this because this is a rare opportunity, probably a lifetime opportunity, that you can prove something in general which is new. And this has not been done for kind of in that generality before. So what you have is arbitrary n times n matrices, and you have a formula for the pseudo-determinant of this ftg, or f star g, and it's in terms of, it's kind of like a dot product in terms of minors. And these are all patterns of size k, where k depends on f and g. In the special case, when f is equal to g, then you have a Pythagorean theorem. So this is kind of like the length of f of the matrix f squared, and it's the sum of the lengths of these minors, and in this case this is just the rank of the matrix. And as I pointed out, you can even put it in the abstract of that paper, this immediately gives you the matrix tree theorem here. What happens is, in the case of graphs, is that, and this f is equal to d, the discrete, you know, just a discrete gradient. In that case, this is actually just either 1 or -1 or 0, so which means the square is 1, and so this actually counts trees. So in the case of the Kirchhoff-Laplacian, you count trees. So this is the number of rooted trees. Pseudo-determinant is the number of rooted spanning trees in the graph. And now rooted means that you have also a root, which you assign just a point as a root, like in a directory of a computer, you have a root, right? The place where you kind of start, but any tree, you can put the root anywhere. And so the number of vertices, if you divide by the number of vertices, you get the number of trees. That's called the matrix tree theorem. Very classical, very beautiful theorem, and it's true for all graphs. So this is true for all matrices. This is true for all graphs. Cayley was doing that first in the case of complete graphs. Famous formula, and this is the matrix tree theorem. Now we will see that so all these kind of things is more general in higher dimensions. Also, there are higher dimensional trees, and everything actually generalizes. That's very exciting. So next I want to say something about this McKean-Singer symmetry, because this is actually just then the link to the torsion. So it's not really needed for that Maze theorem here, but McKean-Singer symmetry is a very important symmetry, supersymmetry, which holds for any network, for any graph. Very universal thing, usually stated like that the Euler characteristic is the supertrace of the heat kernel, and McKean-Singer have done that in the continuum. I did that in the graph case, and I just realized that it's actually, this is a symmetry between the non-zero eigenvalues of the even forms and odd forms, which is just given by the Dirac operator. The Dirac operator d plus d star gives you this symmetry. It's a very important symmetry. So what we have is, this implies immediately that if you look at the superdeterminants, that you can actually, you know, the even and the superdeterminants product of the even and the odd ones are cancelling out. So this is always 1. And that's one of the reasons why this is not an interesting notion to look at just the superdeterminant of the Laplacian, of the Hodge Laplacian. You want to look at the superdeterminant of the Dirac operator. That's what we have done last time. And so in this case this is actually the same thing. So there's this strange K power which comes in, but that telescopes then to the superdeterminant of the Dirac operator. But in the case of the two-dimensional spheres, like here, this is actually just simplifies as the determinant of K over the determinant of K of L2, L0 over L2, and then when you take this Poincare duality, then you get the this is actually the determinant of K, superdeterminant of K over the superdeterminant of K prime, which is the Kirchhoff-Laplacian of the dual graph. So let me just say something about Poincare duality. That's also a symmetry completely different from that symmetry, completely different from that symmetry. It's a symmetry which holds only for discrete manifolds. So discrete manifolds include spheres, but this symmetry, this tree symmetry which we are going to look at, fails completely for manifolds different from spheres, like tori or even very simple manifolds. This fails. It's a very subtle thing. It's a completely different symmetry than this Poincare duality, which holds for orientable, in the case of orientable manifolds. So it's usually stated that the Betti numbers come in these paired Betti numbers, like for spheres 1, 0, 0, 0, 1, or for the two torus 1, 2, 1. So there's this symmetry, but not say for the projective plane, which has a 1, 0, 0, which has 1, 0, 0 as Betti numbers. It's no symmetry because you have no orientability. But what I want to focus on is this beautiful Maze theorem. It's actually due kind of even, about the same time then Kirchhoff was introducing this Kirchhoff matrix. And it's done by Von Stoudt, Karl Von Stoudt, a student of Gauss, completely underappreciated. He was making nice work on projective spaces, on arithmetic of projective spaces, and student of Gauss. And so what he realized, it's something which is actually quite familiar. So it's used in statistical mechanics, for example. You have a spanning tree, and the spanning tree you can look at it at maze. Maybe we look at the maze here. So if you look at the maze with just one entrance, and when the maze is connected, what you have is also the complement is also a maze, and the complement is the dual. It's also a tree. So in the case of mazes, mazes are often trees. Most of the time they are trees, and then the dual maze is also a tree. And so you can pair a tree, and maybe I show a picture here of a sphere, two-dimensional sphere, and I also show the dual, a tree. Took a random tree and draw also the dual tree. So what you do is you have a tree. You take just for the dual tree, you just connect over every of these bridges which are not connected in the tree. It's kind of really a complementary thing. And so what happens is the edges of the tree and the edges of the dual tree add up to the number of edges. So what you immediately have is you have immediately the formula that that v minus 1 plus v prime minus 1, and that's equal to f minus 1, that's equal to e, and that's equivalent to the Euler formula, and that's how Von Stoudt proved in his book. Maybe I showed a book. His book, he has proven the theorem of Euler in this way. Elegant proof of Euler's theorem. Here I just will look at it in the case of two spheres. You have to be very careful what you define, how do you define a polyhedron. So this is explained very well in Lacato's book, Proofs and Refutation. It's one of the... And if this result immediately implies also this result about torsion. So for two-dimensional sphere, the torsion is just the number of vertices divided by the number of faces. So the torsion of a two-dimensional sphere. Very beautiful thing, and you can interpret this in this case, two-dimensional case, as trees. Now, and the point isn't that I'm still writing down that whole thing. This also holds in higher dimensions for higher dimensional spheres or contractible case, so that you can make a statement about even trees and odd trees. And if you define it correctly, the number of even trees is the same as the number of odd trees. So that's kind of the analog of that statement of Von Stoudt. Okay, that's it for today, and wrapping up.